Welcome back, everybody. Now we're going to look at the solution to the diagonal problem. So what is the length of the diagonal that's two spaces away on a polygon? So actually the triangle, it's right there given for you that if the triangle sides are 10, then this diagonal, which is not really a diagonal going through the shape, it's just a side, would also be 10. So that one is easy enough. Now before I switch over to 4 and find out where it's at on the number line, let's see if I can predict what it would be. So let's go over to a piece of paper. So if I have a side length of 10 for a square and I want to find the diagonal length, we already know how to do this using the Pythagorean theorem because this is a right angle. So we have a squared plus b squared equals c squared, or the two legs squares add up to the square of the hypotenuse, so we'll call that d squared. So 100 squared plus 100 squared, that's 100, or 10 squared is 100 plus 100 is 200, d squared. And then to find what number times itself is equal to 200, I could take the square root. So the square root of 200 equals d. And what number is that? Well, we could say, well, this is 100 times 2, and the square root of 100 is 10, but the square root of 2 I do not know, right? It's not a number that can be a whole number, right? So if you put this into your calculator, you'll get something like 1.41, blah, blah, blah. And times 10 would be 14.1. Okay? But is it actually 14.1? No, not really. That's the trick about going into geometry, is that once you... Okay, so let's look at this. So 14.1 looks like it's pretty close there. But let's go ahead and zoom in and see if we can get a decimal approximation for it. So there's 14.1. See, it's not exactly 14.1. Let's zoom in some more. 14.14. Is it 14.14? No. Let's see. I move this down a little bit. There we go. 14.142. 1, 2, 3. Wait a minute. There's not a pattern here. 4, 1, 4, 2, 1, 3, 6. Wow. It's getting to be not really any sort of pattern, is it? This is what we call irrational numbers, that they have no pattern to their decimal expansion, and they actually cannot be expressed as a fraction. Let's go ahead and find out what the label is. That point, I want to find out the value. So it says 14.1421356,237. So there is no real pattern to those numbers. And it even goes out further than that, but the software is limiting the number of decimal points that it could go out. Alright, so that's interesting with the square. What happens with the pentagon? Zooming out again. I went a long ways. Okay. Getting closer. Zooming out. Zooming out. Sorry, I should speed this up. Okay, so we are back with a square, and the diagonal is 14.14. Now let's go to the pentagon. Now I figured this out on a piece of paper, but I'm not going to go through it with you because it's pretty complicated. Let me see. Does that work here somewhere? Yeah, you can see all my scribbles here. I came up with this number. It's 1 plus root 5 over 2, and we call that number phi, which is the golden ratio. And if you put that into your calculator, you get something like 16.1, I think. Let's go look at it. All right, let's open there. So let's go to 5. 16.18. Yeah, that's what it is. So again, you could zoom in and see that it's not exactly 6.2, it's not exactly 6.18, and see that? So zooming back out. And now hexagon's even more complicated to figure out exactly, but we'll just look at it. It's 17.32, and then I tricked you. I said that 7 was 18, but it's not exactly 18. It's 18.019. So as soon as you go outside of counting numerically and you go into geometry now, you end up with numbers that do not have any kind of repeatable pattern. And these are called irrational numbers. So that's what we're going to talk about in this topic coming up. First, let's go ahead and talk about some of those rational numbers that can be expressed as a fraction. So we're going to do those in day 1. Actually, we'll call that day, I don't know, 1.2222 repeating.